is Farhan Khan from the Republic 2.0, and today's topic is the terminal velocity from the second chapter of Edexcel AS Physics, and we're going to talk about it. So first of all, what is the terminal velocity? To understand the concept of the terminal velocity, you have to consider a fog droplet, which is falling downwards under constant acceleration due to gravity. On this fog droplet, there must be, a couple of forces acting on. The downward force by which the earth exert itself, onto this drop, the drop should be moving downwards. The weight is acting downwards. At the same time, there must be two opposing forces. One of them should be the upthrust of the liquid or the medium through which it is falling. We can consider this to be the upthrust. And then there is another force, which would also be the resistive force, and that can be known as a drag force. So eventually, since the fog droplet is a massless kind of a thing, there must be a condition, at a point where the weight would be equal to the sum of the drag force and the upthrust. Or in other words, we can just simply call it when the weight gonna balance out the drag force and the upthrust acting on this fog droplet. In that case, when the weight of this fog droplet would be equal to the sum of upthrust and the drag force. When the weight would be equal to the sum of the upthrust and the drag force. The body, in our case, the body is the fog droplet. This fog droplet would start moving downwards with a uniform or a constant speed. It would start falling downwards with a uniform or a constant speed. So that constant speed is known as a terminal velocity. We call that constant speed to be the terminal velocity. So when it comes to defining the terminal velocity, it can be defined as the constant velocity by which a body falls downward when its weight balances out. When its weight balances out the upthrust and the drag force. Now I'm aware of the fact, some of you might be questioning the fact that since the sum of the forces acting on this fog droplet is almost zero, not even almost, it is zero. The sum of the drag forces and the upthrust is equal to the weight. So why the fog droplet is still moving out downward? This is only due to the fact that the fog droplet is a massless quantity, right? So at the end of the day, it would still be moving with a constant speed downwards because it is about massless. The mass of this droplet can be neglected. So that is why the fog droplet should be moving downwards. So now we need to derive an expression for the terminal velocity, which might be helpful for any question. And it is a very important topic. So first of all, we've got a ball, and we're going to consider the radius of the ball to be r, and the density of this ball can be regarded as rho s. And the liquid through which it is falling, the density of that liquid can be regarded as rho L. And the viscosity, all the other signs you already know, the etas, the radiuses, and all that other things. And now, since for a body to be in terminal velocity, one must satisfy the condition that the weight of the object must be equal to the upthrust acting on an object plus the drag force. So every one of us knows that if you want to calculate the weight, you need to calculate the mass of the solid times the gravitational acceleration. If you want to calculate the upthrust, how would you calculate the upthrust? You need to know the mass of the air displaced by the fog droplet. I'm going to consider it to be some sort of a fluid, so I'm going to call it F times G. This is how we calculate the upthrust plus the drag force. And as according to the Stokes law, the drag force acting on an object should be equal to 6 pi eta RVT, where eta is the coefficient of viscosity, R is the radius of the ball, and VT is the terminal velocity. Now, how can we calculate the mass? There is nothing like a physical balance available by which we can calculate the masses. So I'm going to convert these masses into more portable forms. And I'm going to write their masses as the volume of the solid times the density of the solid times G as it is. And then how would you calculate the mass of the fluid? Volume of the fluid times the density of the fluid times G plus 6 pi eta RVT. So that is how we're going to calculate all these things. Now I'm just going to plug in the values for the volume. Everybody knows that the volume of this thingy would just be 4 by 3 pi r cube times rho s is equal rho s times G. And then again 4 by 3 pi r cube times rho f times G plus 6 pi eta RVT. We just need to rearrange all these variables to get the terminal velocity. So what I'm going to do, I'm just going to move this 4 by 3 pi r cube rho fg to the other side. And I would be having 4 by 3 pi r cube rho s, the density of the solid, times g, minus 4 by 3 pi r cube, density of the fluid, times g, is equals to 6 pi eta RVT. Now, we do know that the common thingy out of all these, both these expressions would be 4 by 3 pi r cube times g rho s minus rho f equals to 6 pi eta RVT. Now, since we are calculating the terminal velocity, so I'm just going to divide both the sides of this equation by 6 pi eta r. So Vt would just be 4 by 3 pi r cube times g times rho s minus rho f, which are the difference of the densities of the solid and the fluid, divided by 6 pi eta. This is how we're going to calculate 6 pi eta r. This is how we're going to calculate the terminal velocity. Now I'm just going to solve them down. So, r cancels out by this r. We'll be having r square left out, and then 2 times 2, and then 2 times 3. So I'll be left out by this 2 pi r square times g times rho s minus rho f divided by 3 times 3 is going to be 9, right? So over here we would be having 9. So 9 pi eta, and that is going to be the final expression for the terminal velocity. So terminal velocity comes out to be, if I just copy my expression over here, I would be having 2 pi r square g times rho f minus rho s minus rho f divided by 9. Pi should also be cancelled out by pi. So I would just be having 9 eta. So what does this expression tell us about? That the terminal velocity is directly proportional to the square of the radius of an object. This is a very important principle that we can use in any theoretical question. Apart from that, the derivation of this thing also comes very often in the past papers. So that's it for today. We just talked about the terminal velocity. Thank you very much.